Good morning, chemistry students. This is Mrs. Krumschreider, and you need to have your Chapter 5 outline out and in front of you. Now, if you are a remote warrior, so you're a virtual learner, and you don't have a printer at home, then you can just take these notes on a sheet of paper. Again, you might want to sort of set up your sheet of paper like the outline ahead of time, but that's totally up to you. So usually students have heard horror stories about chemistry class and how many notes you take. So I kind of want to explain a little bit about why I do that. So I'm really approaching chemistry as getting you ready for college. And in college classes, you are going to need to take some notes from a lecture. Okay, because in college classes, the questions that are on your tests all come from your professor's lectures, not necessarily the textbook. Your textbook is a resource that you can read for additional information, but usually the information comes from your lecture. So you need to be able to take notes. So I realize this is not the most fun way to learn. It's also not the most fun way to teach. However, I've had many students who have gone on and who the first month into college have emailed me and said, Mrs. K, thank you so much for teaching me to take notes because I have to take notes all the time. So I get it that it's not fun, okay? And know that it's not the most fun way for me to teach either, but it is important. Now, at the start, I'm going to write everything down, and you really just have to copy it down, okay? By the time we end Chemistry 1B, you should be at the point where I'm going to be able to speak from a lecture, and you're going to be able to take notes from the lecture without me writing anything down. The other reason it's important for you to take notes is that you will have note quizzes in chemistry on Google Forms. And on those note quizzes, you get to use anything you have except your textbook. So you get to use your notes. And on those quizzes, I'm looking for word definitions from your notes. So it's a way for me to check and see whether you're taking careful notes. So, again, you should have that outline out and in front of you by now. So that outline starts with, 5.1 atoms. And today we're going to be talking about kind of the history of the atom, how we came to understand and know what we do know about the atom. So we're going to start with our very early models of the atom, and we're starting with Democritus. Democritus was from Abdera, and this is in the 4th century BC. So he is of ancient Greece, okay? And so, again, he was kind of the first person to come up with this idea of an atom. So he was among the first to suggest atoms exist. He didn't necessarily call them atoms, he kind of just said they were particles. He thought that these atoms or particles were indivisible and indestructible. So what do we mean by indivisible? Okay, so that means that he didn't think that these little particles could be broken down into smaller pieces. Indestructible, he thought that you couldn't get rid of them, okay, that they always existed. Now, Democritus really had no experimental support for his idea because he didn't follow the scientific method. Okay, so he didn't kind of come up with a hypothesis and make an observation of the world around him, come up with a hypothesis, design an experiment to test it, look at his results and see whether they supported it or not, right? He didn't do any of those things that we do in the scientific method. Okay? He just was looking at the world around him. And so maybe he was looking at rocks, let's say. And he said, oh, look, here's this big, huge rock. And oh, look, here's a little rock. But hey, they look the same. They look like they're made of the same thing. I think that they're both the same thing, but that big one must be made of a bunch of these little ones. So these little ones, these are those particles. Now, if you're looking at rocks, you can kind of understand why you would think that at some point those rocks would be indivisible, that you wouldn't be able to get smaller pieces. And you can also kind of imagine why he would think they would be indestructible. And, Democritus also didn't explain any chemical behavior. Okay, so this was Democritus. Again, long ago. After him, there's not a lot of scientists doing much thinking about this. By about the 1700s, there were only 13 elements that were known. Then, from 1765 to 1775, right? So in that kind of 10-year period, chemists discover 5 new elements. So in all that time leading up to that time, not many elements discovered. But in this 10-year span, chemists discover 5 new elements. And so they said, oh, well, now we know about 18 to 20 different elements. So these early chemists used the properties of these elements to sort them into groups. So to kind of make it easier to keep track of them, they wanted to group them. So there was a scientist by the name of J W Doberheimer. He lived from 1780 to 1849. Know that I'm never going to ask you when they lived or anything like that. I give you that information so you just have an idea so you can kind of put it in time. Okay? And he does this work in 1829. And he is a German chemist. Okay? And so what Doberheimer did was he published a classification system for these elements that they knew about. And he used triads. So a set of 3 elements with similar properties. So he kind of took these 18 to 20 elements that were known about, and he said, we need to kind of have a way to keep better track of them. So he says, I'm going to come up with a classification. He decided to come up with a classification system. And that classification system involved taking 3 elements that were kind of similar in properties and kind of grouping them together. Okay, and so Doberheimer does this in 1829. So that brings us then to John Dalton. He lived from 1766 to 1844. He is an English chemist and school teacher. Now, I want to talk for a moment here about school teacher because we're going to see this describing many of these early scientists. So keep in mind, remember, we're talking about a time when it wasn't real easy to print books, okay? And books were expensive. So the way that knowledge was passed on to the next generation of scientists was they would go to a prominent scientist like John Dalton, and they would work with him and learn from him. And so they kind of call him a school teacher because he taught people, but he taught people who were interested. Okay, so it's not like a school teacher like you think of today where everybody would have had him as their teacher. It would have really just been people who were interested in chemistry. Okay, he does this work in the early to mid 1800s. And really kind of the reason that oftentimes Dalton is the first scientist that's talked about in chemistry is because he actually used experimental methods to transform ideas to a scientific theory. So he didn't just look at the world around him like Democritus did and say, I see these things and they look like they might be the same, and I see big ones and I see little ones, so I think things are made of particles. Okay, Dalton actually used the scientific method, right? So he made an observation. He kind of came up with a hypothesis about why he thought he was observing what he was observing. He would design an experiment to test his hypothesis. He would predict what he expected is the product or the results of his experiment to be. He'd carry out his experiment. He'd compare what he had predicted the results to be to what he actually had happened and decide, hey, was I right or was I wrong and I need to go back and come up with a new hypothesis, okay? So he really kind of followed that scientific method, and he was really is often considered the first person to really kind of follow that scientific method. And he comes up with Dalton's atomic theory. And to do this, he studied the ratios of elements in reactions. So he was performing chemical reactions and kind of looking at the ratios of the elements involved in these reactions. So his first idea, the first idea of Dalton's atomic theory, is that all elements are composed or made of tiny, indivisible particles called atoms. Okay, so again, he's just saying that the elements that they knew about had to be made of some little pieces, and these little pieces he called atoms, and he said these little pieces, they're so small, they can't possibly be broken down into smaller pieces, okay? So they're indivisible. So that was his first idea, the first idea of Dalton's atomic theory, that he came up with this as the result of lots and lots of reactions, studying the ratios of those elements in the reactions. The second idea of Dalton's atomic theory is that atoms of the same element are identical and that the atoms of any one element are different from those of any other element. So basically what he's saying here is an atom of hydrogen is different than an atom of oxygen, which would be different from an atom of iron. Now, to us today, even with the limited amount that you've studied chemistry, you're like, yeah, duh, of course. But in the time of Dalton, this was pretty revolutionary, okay? So this idea that atoms of the same element are always the same. So also what he's saying is, if I have a hydrogen atom in the United States, and I have a hydrogen atom in Germany, and I have a hydrogen atom in Japan, those hydrogen atoms are all the same, okay? That was new. That wasn't something that everybody knew, okay? The way that most people who have studied some science at some point in the past know this to be true today, okay? So it was Dalton who originally came up with this idea. The third idea of Dalton's atomic theory is that atoms of different elements can physically mix together or can chemically combine in simple whole number, and this is a number sign. It was a number sign before it was a hashtag, so it's a number sign here. Whole number ratios to form compounds. So again, he's saying that he knew that there were compounds and that those were different from elements, and he knew these compounds were made of combinations of different elements. Okay? And he said that these elements have to combine in a whole number ratio. Now, that makes sense when you kind of go back to his idea that particles are indivisible. Right? Because if you think particles are indivisible and can't be broken down into smaller pieces, then the only way they possibly could combine is as a whole piece. So a whole atom has to combine with another whole atom. I can't have half of an atom combining with a whole atom. Okay? So he's just explaining compounds are different from elements, but compounds are made of elements. And compounds are made of elements in simple whole number ratios. Okay, so this was the third idea. Again, today we're like, yeah, duh, of course. But this was revolutionary in the time of John Dalton. The fourth idea, okay, of Dalton's atomic theory is that, is that chemical reactions occur when atoms are separated from each other joined or rearranged in a different combination. He also said that atoms of one element are never changed into atoms of another element as a result of a chemical reaction. So basically, he's explaining what a chemical reaction is. He's saying that when I have something that I start with, and those atoms are separated from each other, they're joined together in a way that they weren't together before, or they're rearranged, then I have a chemical reaction. So he's kind of defining what a chemical reaction is here. He says, chemical reaction, an atom has to be separated from each other, they have to be joined together, or they're rearranged. Okay? He also says that atoms of one element are never changed into atoms of another element as a result of a chemical reaction. So what he's saying is, if I have a hydrogen atom to start with, when I'm finished with this reaction, there still has to be a hydrogen atom somewhere. Okay, because that hydrogen atom doesn't become a different element. Now, that was pretty revolutionary because hopefully you've learned a little bit about history at some point in the past, and perhaps you've learned about an alchemist. Alchemists were pretty common in the Middle Ages, and they were kind of early scientists in a way. But what made them kind of popular was alchemists were taking easily, readily available materials, and they were convincing people that they were changing them into silver and gold. Now, why was that important? Because if you had a lot of silver or gold, you were wealthy. Okay, so alchemists for hundreds of years before Dalton had been taking a rock that they would find or that somebody would bring them, and they would change it into supposedly gold or silver because that made it valuable, right? Imagine a big rock. I have a bunch of rocks along my driveway. If I could change those in to gold or silver, like I would be a millionaire, okay? Because I'd have like 3,000 pounds of gold. Okay? What Dalton is saying here is these alchemists, you should not be believing them. They're crazy. Because you can't take an atom of one element and somehow transform it in a reaction and make it gold or make it silver. Okay, so this was kind of a big deal because he's kind of saying these people that lots of people were believing, okay, they're wrong. You can't do that. You can't take atoms of one element and change them into atoms of a different element. Now, what's really somewhat amazing about this is that he was right, all right, about a lot of stuff. Dalton's atomic theory, this idea, this fourth one, that's true today. This third one, okay, that simple whole number ratios, again, that's true today. He was right. The second one, that all atoms of the same element are identical, okay, again, that's true today, kind of with the exception of isotopes, but he really didn't know about isotopes. The only one that isn't true today is this indivisible. Because hopefully, again, at some point in the past, you've learned that atoms are made up of smaller pieces, right? That there's protons, electrons, and neutrons inside of atoms. Now, I feel like we could excuse John Dalton Because remember, even today, we can't see an atom. We can't like go grab a microscope out of the biology lab and take a look at a single atom. It takes a computer and a bunch of special software and such to image an atom. Okay? So again, we're talking about the mid 1800s. Dalton's talking about something he can't see. So I think we can excuse him how he would think something that is so very tiny that he can't even see it. Could it possibly be made up of something even smaller inside of it? Okay, so the only part of Dalton's atomic theory that's not accepted today is this idea that atoms are indivisible. The rest of his ideas, he was right. Okay, so kind of continuing our movement through history in chemistry, okay, we're going to start to talk about the development of the periodic table because, again, at this point, scientists do know about a fair amount of elements. So we're going to talk about Dmitri Mendeleev. He lived from 1834 to 1907. Okay. He is a Russian chemist and again teacher, with that idea being that he would have taught people who came to him and wanted to learn. And he's kind of credited with this work in 1869. Dmitri Mendeleev is known as kind of, if you will, the father of the periodic table. He published a table of elements. So again, at this point, quite a few elements are known about, and there's not kind of a handy-dandy something that has them all listed somewhere. So he says, I think that would be useful. So he creates this first periodic table, a table of elements. Okay? And he wanted a way, so part of, as he's working on it, was he wanted a way to show the relationships among the more than 60 elements that were known about at that time. So he didn't just want to kind of, hey, here's all 60 and put them in the order they were discovered or something. He said, I want to look at these elements, I want to know something about them, and I want to kind of make sure that my table that I put together kind of shows some of the relationships among them. So he arranged the elements in his periodic table in order of increasing atomic mass. So he figured out the masses of these elements and he put them in order of increasing atomic mass. And he actually left spots on his table, so empty spots, and he predicted the properties of the elements that would go there, many of which were accurate. So this is kind of, again, a big deal about Mendeleev. So as he's kind of studying these 60 elements that are known about, and he's doing their atomic mass, he would see kind of small changes in atomic mass, and then he'd see a big jump. And then he'd see a bunch more small changes and then a big jump. And he said, oh, you know what? He's like, I bet there's something that goes in that big jump spot that we don't know about yet. So he actually left an empty spot on his table in those spots where there were those big jumps in atomic mass. Now, again, look at him, right? He's not a real old person when he does this work. He's pretty young. So I want you to think about something. He's saying to all the other chemists that, you know what? We actually don't know all the elements that exist. I want you to think about, if you talk to your grandparents or your parents or some person that's older than you and you say, hey, we don't know about everything that exists in this area that you're an expert in, probably don't believe you. They're probably not very happy with you. So Mendeleev's work was actually not very well accepted at the time, because he was saying to all these people who had been chemists for much longer than he had been, that we don't know everything. And in fact, I think there's something we don't know about that's going to fit right here on my periodic table. And hey, I think it's going to look like this, and I think it's going to have an atomic mass like this. Okay, so Mendeleev's work wasn't real well accepted at the time. It's years later, as they start to discover yet more and more elements, and they go, oh my goodness, look, this element fits right here on Mendeleev's periodic table. And he did a good job predicting the properties and the mass. So later, they look back on Mendeleev and say, oh my goodness, this guy was a genius. But at the time, again, his work is kind of controversial because, again, he's saying we don't know everything. And usually that doesn't go over real well. Okay, so a periodic table is an arrangement of elements according to similarities in their properties. And Mendeleev also thought that some of the masses he had were incorrect. So he thought that some of the masses that he had for the elements were actually not correct. Okay, and remember, Mendeleev is doing all of this work, and he didn't know the structure of an atom. He was still kind of operating on that idea that atoms were indivisible, that there weren't any smaller pieces inside of atoms. Okay? Now, Mendeleev put together the first periodic table. But again, as scientists continue to learn more, they realize that atomic mass, organizing a periodic table by atomic mass, didn't work. Okay, so it's not Mendeleev that says that, okay? It's scientists that come after him, chemists that say, as they discover more and more elements, and they're looking at properties, they're saying, great job, Mendeleev, and you were revolutionary at the time because you predicted these elements we didn't know about, but atomic mass probably isn't the way to organize our periodic table. So, as we continue our march through history, we next come to Goldstein. He lived from 1850 to 1930. He's credited with this work in 1886. Okay. Goldstein observed a cathode ray tube, and he found rays traveling the opposite direction, which he called canal rays. And he figured out that they were made of positive particles. So basically, what Goldstein has discovered is that positively charged particle called a proton. Now, he didn't necessarily know it was the proton yet. They hadn't necessarily called it the proton yet, but he discovered that this positive particle, so we're going to say that this proton's mass was equal to 1,840 times the mass of an electron. Now, to give you an idea size-wise, right, what this is saying is if I have a proton in one hand, it's going to take 1,840 electrons in the other hand to equal the mass of just that one proton. Okay, and so Goldstein again does this work in 1886 by studying a cathode ray tube. We're going to take a look at a cathode ray tube here in just a moment. All right, so Thomson is another scientist. He worked from 1856, or lived from 1856 to 1940. He is an English physicist. And he is credited with having discovered the electron in 1897. Now, again, he was kind of using that cathode ray tube. So he performed experiments that involved passing electric current through gases at low pressure. So, what did this kind of look like? And please know, I am not an artist. Okay? So, what he was doing was, he had a glass tube. Okay, so that's the glass tube. Inside this glass tube is a gas at low pressure. So this is that cathode ray tube, okay? Here, this was connected to a vacuum pump. And he's going to hook it up to electricity. So he puts kind of some metal pieces at each end of this tube, and he connects it to voltage, which just means it's connected to an electric current. And this is a metal disc again. And this one is called the cathode, hence the name cathode ray tube. And we have electrons with a negative charge traveling, okay, in this connection. So this metal disc down here is called an anode. Okay, and kind of this end is a negative charge. Down here on this end, we're going to have a positive charge. So what happened was when he hooked up that voltage, okay, and passed that electric current through this gas in this tube that was at a low pressure, he got light. He got what was called a cathode ray. And he discovered that that cathode ray was made of electrons. So this cathode ray was a glowing beam between the electrodes. So you've actually kind of seen this kind of concept in action before. If you've ever looked at a fluorescent light bulb, right? The fluorescent light bulb has a gas inside of it at low pressure. When you turn on the electricity, so you pass that electric current through it, it starts to glow. Okay, that's kind of the same idea with this cathode ray tube. Okay? And he played with this ray, okay? So this kind of light that he saw, he found that the ray was deflected or pushed away by negatively charged plate, like a metal plate, and attracted by a positively charged plate. So what he did was he took this metal plate and he had the metal plate with a positive charge. And what he found was when he brought that positively charged plate up to this glass tube, this ray moved closer to it. And he also discovered that when he took a metal plate that was negatively charged and brought it up near this tube, that ray moved, and it moved away from, okay, that plate. So what he did is, by doing this, right, is because he knows some things about electricity, he knows that opposite charges repel and opposite charges attract and like charges repel. So he said, well, hey, if I bring this positively charged plate up and I get an attraction, then this ray of light I'm seeing must be negatively charged. And it worked when he brought in that negatively charged metal plate, because now that was pushed away. So he had discovered that a cathode ray was made of electrons. In playing and kind of doing some more experiments, he figured out that the mass of an electron is equal to 1/2000th the mass of a hydrogen atom. And he kind of discovered that in 1900. So, right, initially we talked about the fact he did this in 1897. So he's spending a lot of time on these experiments, and 3 years later, he says that these electrons that make up this cathode ray, they have a mass of 1/2000th the mass of a hydrogen atom. Again, what that says is, if I have a hydrogen atom in one hand, I have to have 2,000 electrons in my other hand to have the same mass. So that brings us to a good spot to stop for today. You don't have any homework, so I hope you have a great day, and I will see you tomorrow.